So, hello and welcome everyone to week 11 of interactive live sessions for the course on fundamentals of convective heat transfer being offered by NPTEL. The course is being instructed by Professor Amaresh Dalal from IIT Guwahati. My name is Debjit. I'm a TA for this course, and like every week, we shall be solving tutorial problems together. So, without further delay, let's jump into question one of today's session. So, question one says that the condition for moderately intense turbulent flow field is given by, and here I is the relative magnitude of the root mean square velocity, root mean square value of the fluctuating components of velocity with respect to the time averaged mean velocity. Is it option A, I less than 1? Is it option B, I greater than 1 but less than 5? Is it option C, I greater than 5 but less than 20? Or is it option D, I greater than 20?
Option B.
Option B. Okay. Let us look at the correct answer, and it is indeed option B. So the turbulent intensity or turbulence intensity, I, it's given by the root mean square value of all the fluctuating components. So what are the fluctuating components? So if we consider this velocity vector u to be a sum of an average u plus a fluctuating part of it u. And remember, u I'm talking as a vector. Okay, let's forget about this. So u is the velocity in the x direction, v is the velocity in the v direction, and w is the velocity in the w direction. The z direction. So these are the fluctuating components. Now, if I take the sum of the squares of these fluctuating components, divide this, take a uh, take the mean of all this. So there are three dimensions. So uh, we have to divide this by 3, and we also have to take the ratio with the average
Mean
time average
velocity.
mean velocity. So if there is one u infinity, we will have to consider this, and we will consider the root of this. So this u infinity in turn is something like u mean square plus v mean square plus w mean square. Sorry, this is not u, this is square. So this is what I represents. Now this I is a sometimes also expressed as the ratio of the standard deviation of velocity to the mean velocity, and this also checks out. So what this means is that there is some fluctuation, but the extent of that fluctuation, is it a fluctuation over a small range or is it fluctuation over a large range, that is represented by this
Intensity.
physical quantity I. So
Yes.
from this I, from the value of I, we can say whether something can be taken as laminar. So if I is 0 or even close to 0, we can consider that to be laminar. If it's less than 1, uh, if it's less than 1, then we can say that it is low turbulence or low turbulence intensity. If it's between this, we
Moderate.
can call it moderately. And if it's greater, then we can say that it's high intensity. And this is somewhere in between. So that's all for this one. So moving on, we'll move on to question number 2. So question number 2 says that consider steady, fully developed but turbulent flow of water in a horizontal pipe. Now, if the Kolmogorov microscale is 0.87 micrometers, what is the mean dissipation rate? Now, this Kolmogorov scale or microscale, it's given by LD equal to uh, the nu cube over epsilon to the power 1 by 4. Now, here this nu is the uh, momentum diffusivity or the kinetic viscosity, and this epsilon, this is the mean dissipation rate.
The main dissipation rate.
Now, LD is given, nu is also given. We just have to find out epsilon. It's simply a matter of algebra.
Yes, yes, yes. So ELD is 0.87.
Yeah, 0.87 micrometers. So
हाँ,
in
it is 10
meters,
to -6 करना पड़ेगा और रेस टू ये हो जाएगा 4 यस 4 into न्यू कितना है 9 into 10⁻⁻7 क्यूब फोर्थ नहीं सर ELT raised to 4 is equal to nu cube upon epsilon. So epsilon is equal to nu cube upon LD raised to 4. Sir, 2 minutes.
yeah, sure. Please take your time.
Nu cube. Actually, आज क्या हुआ? I am in college only, and I don't have a calculator, scientific calculator with me.
So
That's the issue.
I'll try to do this. Let me get my. So the numerator is 27 into 10 to the power minus 21. That's fine. Now the denominator, this can be written as 8.7 into 10 to the power minus 7. Now if I try to do 8.7 to the power 4, that oh, okay, sorry. Sorry. What am I doing? 9 to the power 9 multiplied by 3 is 27. Yeah. Okay, so 9 cube is 729 into this would be 10 to the power minus 21, and over here
Answer is 1.27 raised to 6.
yeah, so if we take that to be 10 to the power 3, because in the question it is said that we have to find it in kilowatt per kg. So then I guess it would boil down to option B,
So
right?
kilowatt means it becomes 1.27, huh? 1272.
Right.
Yes.
Yeah. So if we come back to the calculation, so the numerator becomes 729 into 10 to the power minus 21, and 8.7 to the power 4 is something like
B is answer.
5728.9 into 10 to the power 7 to the power 4. So this becomes minus 28. Now,
Hmm.
doing
No,
this,
this 1272 is answer is correct, sir.
yeah. So
One
this
two.
divided by 5728.9 multiplied by 10 to the power 7. Yeah. So this comes out to be 1.272
Into
into
10
10 to
raised
the
to
power
6.
6 watt per kg. So if we simply convert this to kilowatt per kg, this becomes 1272 kilowatt per kg.
Yeah.
And option B is the correct one. So if you look at the solution, then also option B is the correct one only. And here, I'll simply go back to the previous slide. So the mean dissipation rate, what exactly does it mean? It is basically the kinetic energy which is being lost due to turbulence to become ultimately it becomes heat energy. So mean dissipation rate, this epsilon, uh, this is what the turbulence causes eddies, and those eddies experience shear force, and that uh, causes that kinetic energy to dissipate, right? That kinetic
Yes.
energy is lost, it's no longer useful, and the rate at which it is lost, that is called this mean dissipation rate. Now we can see that for this particular case, 1272 kilowatt per kg, that's not a, an insignificant amount of energy. That's a huge amount of energy that is being lost due to turbulence.
Yes.
Okay. So this is one of the disadvantages of turbulence. But anyway, turbulence is reality in all experiments and practical purposes that we see. Uh, Turbulence is the norm, and laminar flow is quite the exception. So anyway, we will move on to question number 3. So consider the following statements about turbulence. Statement 1 says the most important mechanism for generating and maintaining turbulence is shear in the mean flow. And statement 2 says turbulence dies out due to viscous damping unless some mechanisms keep on pumping energy into the velocity fluctuations. So, which of these two statements is or are correct? Is it option A, statement 1 only? Is it option B, statement 2 only? Is it option C, both the statements 1 and 2? Or is it option D, none of these statements are correct?
Both are correct.
Both are correct. Okay, so if we look at the solution, indeed both are correct. So if we have a look at statement 1, so the most important mechanism for generating and maintaining turbulence is shear in the mean flow. So if we consider the origin of turbulence, let's say uh, we have a perfectly laminar flow through a pipe like this. We can take a parabolic velocity profile like we see in Hagen-Poiseuille flow, and what happens is some above some Reynolds number above Re critical, if there are some disturbances. So let's say a pipe is not perfectly smooth, there are bumps over there, plus moreover, there are pressure waves, pressure fluctuations everywhere. Uh, so due to viscosity, some eddies are formed, and the origin of that is shear. Now, uh, these eddies, they, these disturbances, they grow and then dissipate into smaller and smaller eddies, resulting in turbulence. So, the origin of creating turbulence is basically shear. So another example that we can look at is, let's say, an external flow. Let's say we have a circular cylinder and we have a flow past it. We know that above a certain Reynolds number, vortices are formed and those vortices are shed. So if we keep increasing the Reynolds number, this mechanism of shedding vortices and those vortices again breaking down into smaller and smaller eddies would uh, grow and finally lead to turbulence and uh, chaotic mixing or chaotic flow field. And so that's why statement 1 is correct. And statement 2 says turbulence dies out due to viscous damping unless some mechanisms keep on pumping energy into the velocity fluctuations. So if we do not have continuous source of energy. What is the continuous source of energy here? It is the incoming fluid, which is bringing in more and more kinetic energy. So, in the absence of that, turbulence would ultimately die out. The vortices they would lose their kinetic energy into smaller and smaller eddies, and finally into heat energy, and then uh, there won't be further presence of those eddies or turbulence for for the fact. But this incoming fluid, this brings on further and more kinetic energy, pumping energy into the system and sustaining those uh, turbulent fluctuations. So that's why statement 2 is also correct. So as a result, option C, both statements 1 and 2 correct, is right solution.
Actually, my MTech project was related with this. Actually,
Okay.
in pipe flow, I put some inserts
Okay.
of different shapes with different inclination angles.
Hmm. And what was the goal of that study? To
Heat
disturb.
transfer augmentation only.
Sorry, what?
But heat transfer augmentation
Okay.
enhancement by putting the inserts along the length, right from entry to. So what I have done means it was in post convection.
Hmm.
I have used as air as a fluid.
Hmm.
So I manufactured tube in tube type of heat exchanger. In the center tube, I circulated air from the blower,
Hmm.
and from the surrounding tube, I circulated water.
Okay.
And inside the center tube where air is passing, there I put the one central rod, and on that central rod I have arranged different fins at different angles. Then various parameter, the pitch, the shape of the wings, winglets. I am calling that as a winglets.
Okay.
Then angle with respect to that
Flow.
axis of the
Hmm.
pipe, that is changed, and that parametric study I have done in MTech,
Okay.
and I developed my own correlations for it.
Nice. So
Hmm.
the basic idea was to induce some turbulence with those fins, and then as a result
Yes.
of that, the heat transfer would enhance, right?
But at the same time, there is a pressure drop because pumping power is
Right.
extra. Na?
Right. Right.
So I have done calculations for pumping power also by connecting the manometer, YouTube manometer across inlet and outlet.
Hmm.
So that pressure drop, and by using Darcy-Weisbach equation, I have calculated pressure drop.
Hmm.
So enhancement ratio means what is the benefit we are getting at the cost of pumping power. So that enhancement ratio we have determined.
So an optimal system was designed as a result of
Yes,
it.
yes,
The outcome
yes,
was
yes.
an optimization. Very
Um,
interesting.
yes.
Okay. And that increase in pumping power due to enhancement of turbulence, that can be connected to the viscous dissipation rate that we saw in one of the earlier questions. So that
Yeah.
is the increased energy that has to be pumped in order to compensate for the losses created due to turbulence.
Yes.
Okay, very interesting. We'll move on to question number 4 of today's session. So this is exactly related to that discussion. So in internal flow, turbulence can cause what? Option A, decreased pressure drop, decreased heat transfer. Option B, increased pressure drop, increased heat transfer. Option C, increased heat transfer, decreased pressure drop. Or is it option D, increased pressure drop and decreased heat transfer?
BB.
B. So increased pressure drop and increased heat transfer. So sorry. So pressure drop increases due to the reason that we discussed, that more and more energy has to be pumped in order to compensate for the losses due to turbulence. And but on the other hand, the benefit that we gain is that heat transfer is also increased because there is better mixing between the colder and the hotter layers of fluids, and as a result, the you know, the uh, temperature gradients are wiped out, and that enhances the heat transfer.
Yeah.
Okay. So moving on, we will move on to question number 5 of today's session. So question number 5 says, which of the following is true for energy cascades? Is it option A, the smaller eddies combine to form larger eddies and larger eddies combine to form further larger eddies and so on? Is it option B, the small eddies remain contributing to the disturbance growth? Is it option C, the large eddies break into smaller eddies break down into still smaller eddies and so on? Or is it option D, all of the above?
Answer C.
C. C is indeed the correct answer, and that is what happens in an energy cascade. So, let's say we have a large scale flow and there are very large eddies initially. Those large eddies they break up to form smaller eddies, which give rise to even smaller eddies and so on. And once they reach a critical length scale known as the Kolmogorov time length scale. After that, they cannot further divide into smaller eddies. They simply dissipate that kinetic energy in the form of vorticity uh, as heat. So that's how energy cascade leads to turbulence. So moving on, we'll move on to question number 6. So for turbulent flow parallel to a smooth and flat surface, so it's basically flow over a flat plate, the correct relation for non-dimensional velocity u plus distribution with the normal distance from the wall y plus for the viscous layer is it option A u plus equal to y plus? Is it option B u plus equal to 5 ln y plus minus 3.05? Is it option C u plus equal to 1 by 0.4 ln y plus 5.5? Or is it option D u plus equal to constant?
Option A.
Option A. And it is indeed the correct answer. So let's say we have this flat plate and we have a flow coming in and a boundary layer forming over it. So even in the turbulent region, there is this, you know, okay, let's focus on the turbulent region only. So I'm zooming in. This is the turbulent boundary layer. So even in that region, there is this viscous layer within which the viscous forces much dominate the turbulent fluctuations. And there is a buffer layer in between, and I'm calling this buffer layer, and there is this turbulent layer. So it was shown in the lectures to derivation that within the viscous layer, the u plus is equal to y plus. Uh, so the velocity actually has a linear profile with respect to the normal distance from the wall, and in the outer layer, that is in the turbulent layer, there okay, so another thing over there was that this mu plus mu t, nu plus mu
Hmm.
t. Nu was the normal viscosity, and this was the turbulent viscosity. So in the viscous layer, this one dominated and over this one, the turbulent viscosity, and in the turbulent layer, this one dominated over the shear forces. Uh, so that's what led to simplification of the equations. But nonetheless, the final solutions were like this. So u plus equal to y plus was true for the viscous layer, and u plus equal to 1 over zero point 0.4 ln y plus
Turbulent.
5.5. This was
Turbulent.
for the turbulent layer, and in the buffer layer,
Center.
which actually connected the two inner layer to the outer layer in that region, we can use this correlation that u plus equal to 5 ln y plus minus 3.05. Okay, so moving on, we will move on to question number 7 of today's session. So for pipe flow, let's say that L1 is the hydrodynamic entrance length for laminar flow, L2 is the thermal entrance length for laminar flow, L3 is the hydrodynamic entrance length for turbulent flow, and L4 is the thermal entrance length for turbulent flow. Now, considering that Prandtl number is much less than 1, pick the correct option, which are different orders of this length. Is it option
When
A?
saying Prandtl number much less than 1,
Yeah,
delta by delta T is less than 1. Means hydrodynamic boundary layers are lesser than thermal boundary layer.
thermal
For
layers are smaller than the
means velocity boundary layers are below thermal boundary layer.
correct.
प्रांडल नंबर लेस देन 1 है तो
Hmm.
अभी सोचना है कि लैमिनर एंड टर्बुलेंट में किसका
Yeah,
बाउंड्री लेयर कम होता है.
correct.
इस टर्बुलेंस में एंट्रेंस लेंथ कम रहेगी सर.
True.
मीन्स ना के बराबर भी पकड़ा तो भी चलेगा. टर्बुलेंस में एंट्रेंस लेंथ कम रहेगी तो
So from here we can say that
well,
hydrodynamic lengths are smaller. So L1 and L3 they would be somewhat smaller than L2 and L4, right? Which are the thermal layers. Now thermal boundary layers. Now sorry, the thermal entrance lengths. Now in case of turbulence, that entrance length gets even smaller. So among L2 and L4, which one would be smaller?
L2 is thermal entrance length for laminar flow and L4 is smaller.
Okay, did I do this correctly? No, this is incorrect. So they will be larger. So L2 and L4 are smaller. They are the thermal entrance lengths. Now among them, the turbulent one would be even smaller. So we can say that L4 is smaller than L2, and over
Then
here,
L3 and then L1.
yeah, we can say that L3 is less than L1, and they are greater. So 4, 2, 3, 1. This would be the
D.
correct order. So
Option D.
option D indeed is the correct answer. Okay. So that's all for today. Thank you. It has been a good session, and we will meet again next week, and that would be the last session.
Last session.